So when I look at aspartate or aspartic acid, there's only one site where you can put an extra hydrogen, and that's on the amino. So that's why we get the NH3 plus here. So there's only one plus one charge and no other zeros no other negatives. So that's why our overall molecule has a charge of plus one. This is the most acidic form, got the lowest pH or pK, however you want to think about it. So we're going to add a base to our solution of this amino acid. We're going to get more and more basic. And eventually, once we hit the wall of 2, we're going to lose a hydrogen. The 2 is kind of like that cardinal value that you have to remember to attribute to the carboxylic acid that's attached to the carbon of the original template of the amino acid. Does that make sense? Yeah. So for the carboxylic acid that you see for every single amino acid at around a pH or pK value of 2 is when we're going to lose that hydrogen. Which explains this COO minus negative on the top. So now we have one positive, one charge, one negative, one charge. They cancel out to make 0. That's why the overall charge of our molecule is 0, neutral. This is the zwitterionic form of aspartic acid. So I gave you guys the pKr, which is just simply the pK value associated with the R group or the side chain. And as we look at our side chain, we see it's a carboxylic acid. So that's how we know it's kind of like it's a giveaway for whether we can take or add a hydrogen. So as we add more base, we're going to hit the wall of 3.6, which is when the side chain loses its hydrogen. So that's why we have 2 carboxylate groups here, 2 negative ones. One's a positive to cancel out one of the negative ones. The overall charge on the molecule is negative 1. However, you don't stop there because there is one other group that's ionizable, and that is the amino group. The amino, or the alpha amino, if you think of it that way, that's part of our template amino acid. Once we hit the wall of 9, that's when it is going to lose its hydrogen, which is why we went from an NH3 plus to an NH2. There are no longer any positive charges anywhere on any group on our amino acid, only 2 negatives, giving our overall molecule a negative.
So in theory, we just keep going until there's no charges on.
How long does it last for?
Until 250.
250? Because we gotta fix the air conditioning, but we gotta see them when to do it. So, we'll wait.
Thank you. I really appreciate this. Very
Yeah, it's do just one room at a time, man.
Thank you. I really appreciate it.
All right.
So yeah, you were saying?
Never mind. My question didn't make sense.
No, I have time.
So are we just like we're removing hydrogens?
Yes, you're removing hydrogens as you move through each stage of the charge diagram.
I think I'm also just what are these numbers with under the those?
These are the pK value, the specific values at which you lose those hydrogens.
Okay.
We need those to calculate the isoelectric weight.
Gotcha.
I have 2 questions I think. So does it matter the order you deprotonate it?
Yes, that's what the pK values tell you, in which order, what gets deprotonated first. So this pK value of 2 is associated with this carboxylic acid. That's why this hydrogen is stripped first, and not this one or this one.
Okay, and then the pKr, that's specifically when the side chain.
The pKr is the pK value of the R group. Or the side chain. So this CH2 COOH is the R group or the side chain of our amino acid, specifically for aspartic acid. So the pK value of pKr at which it will lose its hydrogen is 3.6.
Okay, and then, so when you see examples of it starting with +2, is that when there would be
That's the
multiple
number he gave
NH2s on there first?
Yeah.
He gave us
Yeah, let's say this for lysine.
So 3.
Lysine ends in an NH2, and then you can protonate that to make an NH2 plus, as well as the alpha amino, which would also be an NH2 plus.
So is that
So
when
it'd be a
it says
+2
3
charge.
pKs? Is that the difference or not?
I mean, there's no true difference. I think there's only multiple pKa's depending on the number of ionizable groups. So for any one amino acid, the alpha amino, alpha carboxylic group are always going to be at least 2 pK values, and then the R chain would add on a third. So does that answer your question?
Is NH2 not the only ionizable group? Is that what you're kind of saying?
I mean, NH2, COOH, SH,
So there's more that can.
there's more. Yes.
Okay.
Can you just explain the loss of charge on each again? I'm sorry, it's probably easy, I just missed it somehow,
The loss of charge,
or like what charge you're starting with, and then like,
So we start off with a +1 because the only, like, this fully protonated form is the NH3 plus that has an isolated +1 charge. And then we're gonna be losing hydrogens. The first hydrogen to be lost is from this alpha carboxylic acid group, and that makes it a -1 charge, and that the negative one and the positive one cancel out, which is why it turns to 0. And then we further deprotonate our amino acid. The R chain, the R side group is going to lose its amino acid, its hydrogen, sorry. So then you have 2 negatives and 1 positive, giving our overall molecule, or overall amino acid, a charge of -1. We're gonna further deprotonate it, and we're gonna steal a hydrogen from the amino group, and then we're gonna have no more positives and only a -1 on each carboxylate group, giving us an overall amino acid charge of -2.
okay, that makes sense. Thank you.
How do we know which hydrogen gets removed first? Like
The
does the
pK
order-
values tell you that.
Oh,
So for the alpha carboxylic acid group, it's always for every single amino acid going to be around 2. So that's why I wrote 2 here. I gave you the pKr because that's the pK value associated with the side chain. So that's going to be next. And then for the alpha amino, for every single amino acid, it's going to be around 9. So that's why it comes last. It's like a number line.
When you say alpha carboxylic group, like, is that like a part of the classification of them, or like?
Right? So every amino acid starts off with the same basic template. We have carbon, going to have 4 groups on it. It's going to be our R group that gives the amino acid its functions. We're going to have a hydrogen at the top here. We're going to have a carboxylic acid, and then we're going to have an amino group. This carbon, from organic chemistry, we give this an alpha denotation. So this is the alpha hydrogen. This is the alpha carboxylic acid. This is the alpha amino. And then just have a section.
So does that mean, because when you said those numbers, the 2 and the 9, they always relate to any alpha carboxylic group, or do all amino acids have those?
All amino acids have alpha
So-
amino and an alpha carboxylic.
The 2 and 9 apply to all of amino.
All of them.
Okay.
Wait, can I take a picture? So that's how you start for every amino acid?
Every single amino acid has this structure. This R group changes the amino acids, like where it is. Alright, anyone else want to take a picture?